Hello and welcome back. In this video, we want to talk about the idea of simulation. You might have already seen simulation without recognizing it. Every time you play computer games, any game, that's using simulation. Without simulation, it's not going to be very fun. And you probably wouldn't then hear about that game. Every time you watch a movie, a cartoon movie, that is computer generated, that looks very real these days, that's also based on simulation. And anytime you live in a building, in Singapore at least, uh, that building would have been designed based on computer assisted design software that would provide some sort of simulation, okay, on various things. For example, the stress tolerance level of the building, and in certain cases, simulating shaking. All right, the forces by the winds, because in Singapore the wind can be quite strong. Would it shake a high rise building, and make it swing so much that it becomes unstable, right? So the stress simulation in finance, right? There is also uh, simulation scenarios where we ask, what if the interest rates keep getting higher and higher and higher? Now, of course, we're not talking about mathematical extremes like interest rates reaching infinity, right? That will be insane. We're talking about interest rates going 0.1% higher, 0.5% higher, but it keeps going up. Can the society, right, handle it? Can the bank's asset, right, and its current health, financial health, handle it, right? If the debt keeps getting into bad debt situation, people not being able to pay up, can the bank handle it? Now, of course, we are talking about uh, a sort of a virtual situation, a planning situation. So I've already used the words where simulation comes out a lot, right? Where we want to talk about an imagined situation that is possible but not too probable. For example, financial crisis. Yeah, how would banks behave? How would mortgagers behave? That means people who borrow money from the bank. Uh, Not everyone will go into bankruptcy. Not everyone will have the financial ability to withstand another financial crisis. So we need some sort of a randomness, right? So all these become problems that need some sort of a simulation, right? We ask about planning also. What if this? What if that? And for climate analysis, for example, what if climate destruction continues and the tides in Singapore's waters keep rising, right? And so if they rise, how fast do they rise? We don't want to talk about an end of world kind of scenario. Oh, we'll be rising so fast, right? But like 10 stories high within a day. I mean, not those are not impossible, but then it's not planning anymore, right? It's more like a Hollywood end of world movie theme. What we are doing for planning is like for the next 10 years, 20 years, 30 years even, how fast, how furious will the tide be rising? And then what are the countermeasures? Will the countermeasures be effective? How much money do we need? And if we need a lot of money, do we have the ability to do that now, or should we tighten our belts to save up now? So all these have got repercussions, provided of course the simulation is realistic. So today what we are going to do is to talk about what is the core ideas or theories or even mechanisms that are at work, right, in simulation. Three things: CDF and InvCdf. These are statistical definitions, and we want this part of the statistics theory to help us understand simulation. Next is random numbers. What do you mean by random numbers? Why do we need random numbers, right? And they are core. They are always needed in anything that you call simulation. Without random numbers, we cannot do simulation properly, and the simulated results will not be reliable. And finally, we look at some applications, some of which I've already alluded to, right? And basically, after talking about the core tools that we use to perform simulation in all simulation, whether it's virtual reality, uh, movies, games, right? They all involve these ideas. And then we look at how we apply them in business domains. So the core idea underlying everything about simulation is the notion of cumulative distribution function. This idea of cumulative distribution function, CDF, and is defined as adding up all the probabilities from capital X equals to minus infinity to capital X being equal to a specified constant. Here I write it as little x, for example, -1. Okay, so any constant. So we write this way: CDF of x is adding up, right? So P of capital X less than or equal to x is adding up all the probabilities of capital X ranging from minus infinity to the given constant little x. Inverse is the inverse of that. We'll come to that in a while. So over here at the bottom right, we have a PDF chart. PDF chart is just the probability density function chart where the height is the PDF or the density. That means if we have a very tiny little strip, vertical strip, how much probability is there? So obviously at the mode here, a tiny little strip will have more probability density than another equal width strip situated at -1 or 1 on the rate curve. Yeah. So if we look at the blue curve, since we are talking about blue curve, let me change color to blue. If we're talking about blue curve, we ask what is the CDF of -1? What is the CDF of -1? So the way it goes, go by definition, is to add up all the probabilities from minus infinity under the blue curve all the way to 1. Not exceed all the way to -1 because we say -1, right? So not exceeding -1. So already I'm drawing the area under the graph, which is requiring us to perform integration from integration of the function PDF from minus infinity to -1 in order to get the area, because area is the probability, and that would give us CDF of -1. That is if you're working on a PDF chart. On top of the PDF chart, however, if you have a CDF chart, that means the chart reflects the CDF function. Height is the CDF. And you align the -3s together, the -2s together, and so on, the x-axis, right? All the scales are lined up. Then all we need to do is do a table lookup. That is, what is the CDF of -1? We look at -1, where's my x? Okay, -1 over here. And we go up to reach the blue curve, and then we extend it horizontally to check what is the value on the y-axis. Let's say the value is 1. Right? So 1 here represents 0.1, and so we can write down straight away 0.1. So that's just a table lookup. We don't have to do integration. So that is the behavior of the CDF graph here. Now, obviously, you're going to say, all we need is just to let computer do the integration, right? In R, in Python, we can do that rather easily. without going to the details of calculus and all that stuff, right? And that's true, but that's still going to be very computationally intensive. So if you imagine a Hollywood movie like Lion King or Toys, right? All these very highly simulated graphic screens, every pixel needs to be calculated. So if every pixel that is being simulated needs a lot of integration calculations, not that it's impossible, it's just that it's going to be requiring a lot of high-end computers, thereby increasing the costs a lot, or taking a lot of time because it takes a long time for the slower computers to do all these integrations and calculations, intensive computations. Then it would not be very feasible as a technique to uh, produce a new market of demands for movies, right? And in various business situations. So not a good way to go. Fortunately, it's mathematics. So there are always improvements in various uh, theories by applying other theories and ideas. So the idea is that when we have CDF like this, CDF, where is okay, so when we have a CDF chart like this, calculating the forward, that means given a number, given a -1, right? Forward calculation of CDF is a table lookup. And then we come to inverse CDF. The inverse CDF is the reverse. So if I were to tell you, you know what? The area under the PDF curve from -infinity to some number, I don't know what, but the area is 0.1. Can you tell me that number? Now, of course, in this example, we can, because we start off knowing that the answer is -1 in the first place, right? But what if I say 0.12? What if I say it's 0.55? You wouldn't be able to tell me. And if you stick with the PDF chart, you have to do the inverse of integration. That is going to be rather challenging. It's not exactly differentiation because as a function it would be, but then as a numerical example here, for that particular value, how are you going to do that? But for the CDF chart, it is the concept at least is a lot easier. For example, if I tell you the y-axis is 0.1 for the blue curve over here. For the blue curve, if I tell you the y-axis is 0.1, can you tell me what is the right limit of the area happening at the bottom? We know the answer is -1. So what we do is we kind of shine a laser beam horizontally, starting at 0.1, all the way to hit the blue curve, right? Because we are examining the blue curve itself. Then it gets reflected downwards and it hits -1, so that will be our answer. And you can see that it is a one-to-one situation, don't you see? Yeah, because when -1 shoots a laser beam upwards, it gets reflected reflected by the blue curve to the y-axis 0.1. And so if we shine a laser beam backwards from 0.1 on the y-axis, we expect it to hit -1 as the answer. And now for my other questions. What happens if it's 0.55? We just shoot a beam here at 0.55. It hits the blue curve, probably slightly larger than 0 or around 0. Our answer is 0.01 maybe, right? So slightly larger than 0 itself. And that will be our inverse CDF function. That's it. It's like a reverse lookup of the CDF chart. Okay, so now we have this chart concept to help us think about what is the meaning of inverse CDF. It's just shining that beam starting at the y-axis. Okay, so now the third point here is to say that CDF function is not a fixed function. It's not like sine and arcsine finish. You know, the pair is arcsine is the inverse of sine. That's the inverse function for sine. But then we also have other trigonometric functions, right? So we have cosine, and the inverse function for cosine is not arcsine, it is arccosine. And for tangent, it is not arcsine nor arccosine, but it is arctangent. So InvCdf is just the meaning itself, it's generic meaning. What is the actual mathematical function depends on the shape that you are talking about, the distribution you are talking about. So over at the bottom right, we have a normal distribution here. Then the inverse CDF function will be a inverse CDF for the normal distribution function. So we should be more specific, more careful at stating what distribution are we talking about when we say inverse CDF. So this is important. But of course, when the context is clear, like for example, we're discussing now, right? And I'm only talking about normal distribution. So it is not ambiguous when I talk about inverse CDF. It has to be talking about the normal function itself. Okay, normal distribution itself. All right, so that is in a very simplistic way, right? The idea of CDF and inverse CDF. We want to use the inverse CDF function. Okay, and of course, to understand inverse CDF, we cannot discard or ignore CDF because that is the other side of the story. So now that we know well these two functions of a given distribution, let's just, by way of example, look at three categories of distributions here. I'm going to just talk about these three because they are easy. First of all, they are also commonly encountered, and the table distribution is very practical. That's oftentimes what we see and what we record in real life when we perform a lot of measurements and maybe plot a histogram in Excel, in R. We'll get a table distribution basically, right? So there are finite numbers of X listed out as an Excel table or as a data frame in R. Basically, that's the most common form of representing distribution that we will see in practice. We cannot ignore some of the important mathematical standard functions like normal distribution. And that is like everywhere, right, in all subjects. So we have to talk about that. And finally, another standard mathematical function that we commonly encounter and that is quite useful is the uniform distribution. So let's take a look at the discrete probability distribution function. Discrete because there are fixed finite number of items in the x-axis, as opposed to, for example, the x-axis for normal distribution. There are infinitely many possible values for x. So here, 9, 10, and 11. Let's just give it a business context. For example, these days are very hot in Singapore, so I'm a sugarcane juice seller. To sell sugarcane juices, I need to buy boxes and boxes of sugar canes, right? And then, of course, use them. And let's say I randomly count or select a day to count the number of boxes of sugarcane juices I have used. So I pick a day and I counted for that entire day, I used up 9 boxes. I randomly pick another day, I got 11 boxes. Another day, I got 10 boxes, and so on. Yeah. So if you can imagine that picture, and let's say I don't have infinite days, right? I pick 10 days, right? First, I counted 9 days, 9 boxes, sorry. So I put a little Lego block here, right? The next randomly selected days, I counted for the whole day 11 boxes, right? Yeah, that's how we plot histogram anyways. Another day, I got 10 boxes. Another day I got 10 boxes, right? And you can imagine how I start to see the distribution as I put more and more Lego toy blocks on top, right? And because 10 boxes tend to be my average mode median uh, number of boxes of sugar canes that I used for sale, I get that more frequently, right? Obviously. And so after 10 days, I have 5 counts of 10, 2 counts of 9, and 3 counts of 11. You can follow that, right? Every time I see 11, I put another fixed height Lego toy block on top. And that's how I get this distribution, right? And of course, the y-axis was originally count. So it's 2, 5, and 3. I just divide by the total, and I get the probability equivalent. Assuming that this ratio, this proportion, continues into the future, then this histogram will just be telling me my probability of encountering a 10 box day is 50%. 11 box day is 3%. Right now, yeah? So that's how I get this distribution. Now for the calculation of CDF of 10, let's go forward first. The definition, add up all the probabilities. For discrete probability distribution, the height is the probability. So we say, let's try to look at 9. The probability is 0.2, so we add that. 9 is less than or equal to 10. What about 10? It is also less than or equal to 10. So we have to add the 0.5 as well. So we add that, and the answer is 0.7. What about the inverse CDF? Well, in this case, of course, it would be 10, since CDF of 10 gives rise to 0.7. So what about something else, right? How about inverse CDF of 0.625? For that matter, it can be any real number between 0 to 1. Even though our x values are discrete, right? Our y-axis is supposed to be a continuous interval from 0 to 1. So what about this? How do we calculate this? We go by trial and error in a way, right? So try x equals to 9. I want to say that my answer is 9, right? But 9 is adding up to only 0.2. I've collected only a 0.2 probability, which is not matching 0.625. So we include 10 as well. So by the time we reach 10, right, we would have accumulated 0.7. So this is the first time we are larger than or equal to 0.625. So our inverse is 10. So answer, it is also 10. And that's not wrong, because even though inverse CDF of 0.7 is 10, that doesn't mean that inverse CDF of other numbers cannot be also 10, right? So this is very normal, and is showing you how you can easily calculate this. In software, of course, we will also do the trying. It's more like searching, right? So we keep the search by keep adding using Excel or R to do this, right? So, but then the thinking is the same. You keep looking up. You cannot have a formula, because every bar, let's say from 9 to 10, you go by 0.3 upwards, but it's not like linear or predictable into the future. The next moment, it drops by 0.2, right? So the height is it can be anything, right? Especially if you have more x values here. So you just have to do a try or a search approach, and that is how we will do it, either manually or in computer. Next, when we look at normal distribution, something we have seen earlier on, but let's get a little bit more specific and numerical. Suppose capital X, the random variable, okay, has a normal distribution. So we write X follows, the tilde sign, same is pronounced as follows normal distribution, but you need to have two numbers to specifically point at a particular normal distribution. Those two numbers are the population mean and the population standard deviation. So let's say X follows normal, right? Population mean 10. So that in other words, let's say my sugarcane juice business, uh, the consumption of number of boxes per day follows normal distribution. And the average is 10. In other words, most of the days, I will use up 10 boxes of sugar canes. Okay, and there's fluctuation, sometimes 9, sometimes 11. But when it is normal, it can also mean that there's some probability that some days I have only 8 boxes. I use only 8 boxes. Some days I use only 2 boxes. That's what it means when you have normal distribution. But there's also on the right side of the mean. That is, some days I may use 20 boxes. Some days I may use 50 boxes, even though the probability is very, very small. But that is non-zero. Okay, so let's say x follows that. All right, what is the inverse CDF of 0.625? Same question, but different distribution. And this time round, we need to make it more specific, right? Because the inverse CDF here is not a table lookup. It won't work. There's no table. What we need to do is to use mathematical software, because it's going to be very complicated, and we use Excel's norm.inverse. In R, we will use QNorm, for example, to inverse out. That means I give you the CDF probability based on this particular normal distribution, 10 and 1. Give me the right side of the area from minus infinity to what number? That's the right side of the area. Right. Answer is 10.3186. A little bit different from 10, right? Because we started off with a discrete table in the first place, and here we have a infinitely continuous x-axis here. So 10.3186 is the right mathematical answer, although in practice we won't be seeing 10.3186. It's either you open the 11th box or don't, right? So it will be either 10 or 11. It won't be 10.3186. But that's not bad, right? Because we know that it's going to be like in between 10 and 11. So we can make sense of it. Turns out that it is also then useful. And finally, for uniform distribution, same thing now. We will say that x follows uniform distribution from 7 to 11. 7, 11. So notice that there are two numbers here to uniquely define which uniform distribution we are talking about. But these two numbers are different from the normal, right? So these two numbers are more the left edge and the right edge, where the random variable, capital X, has probabilities. So uniform distribution, you understand that it is uniform, right? The probability, or in this case, the continuous probability densities, they are the same. Uniform means the same, constant. So whether x is equal, in other words, capital X equal to any value from 7 to 13 will have the same probability density, right? The height, right, of 1 over 6. So now let's ask, what is the inverse CDF of 0.625? Same question. How do you answer? First of all, recognize that we can see the probability by looking up the area. So the area from minus infinity to x, that's the definition. But for this particular uniform distribution, minus infinity until 7, it has 0 probability. So we might as well just directly start adding from 7 onwards. Yeah. So the shaded gray area here is representing the CDF of x. And we know that this area, the gray area that's shaded here, has an area of 0.625. So then the question is, what is x. But that's easy because it's like solving a one equation, one unknown problem. The area of the gray area, the gray shaded area, is the length, where is my length? Length times height. So the height is constant, it's 1/6, and the length is whatever x is, minus 7. And that has to be equal to the area given to us. So we solve for x and we get 10.75. And this is illustrating, right, that when the CDF function is easy, has a simple formula, we can just invert the function, like make x the subject of y. Then we will be able to directly calculate with very good precision. But when it is complicated, like normal distribution, other distributions like chi-square f, which are super complicated, right? Then we will probably use computer software to do numerical integration or search or various stuff, right? I mean, it's beyond our need to use manual methods. Next, all these are good about InvCdf, but what do we do with it? Right. So here is, in a very, very simplified summary form, the steps that we do to get random numbers. Because random numbers are the ingredients to do simulations or to obtain simulated results. Without random numbers, we basically don't do much. Okay, we can't do much. We can't get any outcomes. We can't get any insights. So how do we get random numbers? First thing first is random numbers are not chaotic numbers. They are not out of control numbers. They are random based on our desired distribution. Right? So I want a distribution, I want a set of random numbers that when I plot the histogram on them, I get a normal distribution. How are you going to generate those random numbers? You cannot throw a dice, because if my normal distribution is centered at 100 with a standard deviation of 10, you throw a dice is 1 to 6. It will never get to 100. So what are you going to do, right? And here is basically a recipe that will guarantee us that we will get the kind of distribution, the shape of the histogram that we desire. First, generate a uniformly distributed random number, real number, from 0 to 1. Can be 0.35, 0.76, 0.45, 0.789. And once we have that, we find the InvCdf of our desired distribution by evaluating it at Q, the number that was generated. By doing so, repeatedly, we'll get the desired random numbers, such that when you plot the histogram, you get the distribution shape that you want. Okay. Some of you might be thinking, wait, we had to generate random numbers in order to get random numbers. Why don't we just use uniform, right? A few questions immediately will point you in the right direction. Our desired random numbers, for example, it may be uniform distribution centered at 100 and a standard deviation of 10, let's say. Huh? And if you have a uniform distribution, forever the number will be 0 to 1. It will never be reaching to as large as 100. So the scaling of the numbers, right, will not be appropriate. Then you say, well, why do we times 100? True. Then you will get 0 to 100, and you won't get anything larger than 100 or even to infinity. Then you say, why don't we change the uniform to 0, infinity, right? That's where we need to become practical, because here, uniform distribution from 0 to 1 is, in a way, easily generated. Okay, easily generated for two kinds of meanings of easy. One is it is easy to design into the chips and circuitries uniformly distributed random number generators between 0 to 1. So that's uh, relatively easy. Relatively easy means it's cheap, right? It's not going to cost a lot to do that. If it's going to cost a lot to do that, then it would not be so feasible. It would not be so economical. Then the whole idea of using simulation will not be so popular. Yeah. So it is cheap to design it. Number two, when we run random numbers, uniform numbers from 0 to 1, when we run that circuitry to generate such uniform numbers, it is taking very little computational time. Okay, so it's very fast, very little burden for the CPU to generate random numbers. Again, if not, then we have a lot of trouble, right? If generating a simple, uniformly distributed real number from 0 to 1 takes 10 seconds for the CPU to be sure that it is doing all the decimal places correctly, then we have a problem. Because in, for example, a flight simulator, we need hundreds and millions, if not even billions, of random numbers in a minute. And so if you take 10 seconds to generate one random number, then flight simulation will not occur. Real-time flight simulation will not occur, and pilots for training will have to really fly the plane. And because they are trainee pilots, there will be higher risk, right? Higher insurance, therefore, more expensive, and there will be fewer pilots in the world, and so on and so forth, right? So there are consequences. And so, fortunately for these two things, right? Easy to build a circuit, easy to run the circuit. It is not computationally intensive. So we can easily, therefore, generate billions and billions of high quality, uniformly distributed real numbers between 0 to 1. High quality means that when you plot a histogram of these generated random numbers from the circuit, it looks almost flat, right? No spikes on any side, because any spike would mean that there's a bias towards generating higher numbers or lower numbers, then we have a problem. So uniformly generated random numbers from 0 to 1. Second is the role of the inverse CDF. Now, just to draw an analogy for easier or better understanding, think of uniform distribution here from 0 to 1 generated from the circuit. Think of those numbers as rays of lights that are not focused, just general bright light, right? So if we want to focus all the light energy to a particular point, right, we need a lens, right? Have you tried that before? Use a lens, one side point to the sun and the other side will show you a spot. And to get focus, you need to move the lens up and down a little bit so that the spot is very focused, and after a while it may even generate a lot of heat, right? So inverse CDF is exactly like that. It is accepting the raining down of a lot of numbers, random numbers, uniformly distributed between 0 to 1, and it is focusing them, right, onto the shape that we have specified. So it's going to like distribute them in such a way that it's no longer uniform, but it is looking normal. It is looking chi-square. It is looking F distribution. It is looking like a table distribution that we assigned. Right? So that is the way, the role that inverse CDF works in order to produce the desired distribution. Now, why would we want a particular shape of distribution? For example, why would we want a normal distribution with a large standard deviation? Because it's 10% of the mean. Well, because we are trying to mimic an old machine, a clunky machine, right? That sometimes take a little bit longer to stamp a metal, sometimes take a little bit shorter, right? Because it's malfunctioning a little bit to mold the metal, thereby producing irregularly molded uh, flow units, metal pieces, and some will fail the quality control checks. We are trying to mimic this situation, right? And then continuing from that simulated old molding machine, we might then estimate the defect rate or yield rate, and then estimate the losses coming out from the continuing use of this old machine for another half a year before we buy a new machine. So all these planning, they will help a lot. But if you use a fixed proportion formula, okay, like, I declare that this old machine, 20% of them will be defective. This somehow shows that you already know the answer, right? You already know the answer. So if you want to sort of talk bad and you want to renew this machine, you want to buy a new machine earlier, then you just declare that, this old machine has 50% defective rate. It's more like you are asserting what you imagine as reality. So how convincing is that kind of argument, isn't it? Yeah. But then if you say, look, every uh, uh, every outcome, every result of this old molding machine has a uh, you know 10 to 15% probability of producing a defect, right? And depending on the time of the day and all that, so you are trying to describe the observed behavior of this molding machine more accurately, but without making a conclusion about the overall production, the defective rate of this old machine. Then we describe all the factual micro observations, the details. Those are factual, those are agreeable by everyone in the meeting room, right? And then we say, let's run it and use computer to assume it runs for another 100 days, runs for another 1,000 days, and see what happens. So when we do that kind of simulation, the outcome is not some exciting Hollywood movie. The outcome is not a very attractive game system, but the outcome is maybe just a percentage. Like 12.35% of the production will be defective. That number is an outcome that describes the overall macroscopic behavior of the old machine. Macro in the sense of after running many days, after stamping 1,000,000, right, units, what will be the defective rate like, right? So that is the macro outcome which we cannot carry out in reality because it's kind of destructive. After waiting for 100 days, the 100 days are gone and the machine gets even older, gets even more clunkier, right? So it's a kind of non-repetitive observation or measurement, and so we cannot risk that, right? So how are we going to make decision without making a measurement of the old machine? Well, simulation. That's the reason why, right? Okay, so back to our slide here. Now that we understand some examples, right, of the need for having a prescribed distribution of random numbers, then we know that InvCdf is the tool for us to get that. And specifically, right, we need software to do that in a quick and massive manner. In Excel, our source of random numbers between 0 to 1, real numbers, uniformly distributed, is the function called rand without taking any parameters. So you feed the rand into norm.inverse. So rand gives you Q, a number between 0 to 1. You feed that into norm.inverse. That is the InvCdf for normal distribution, how it's being spelled in Excel, right? With your specified mean and SD. So we will specify 100 here, and SD is 10, right? And basically, then we are done. If it is uniform, then the inverse CDF function is just A plus B minus A times Q. This is the inverse CDF function for continuous uniform distribution from A to B. And for a particular table, the Excel way of saying inverse CDF for a table, discrete table, is VLOOKUP. So VLOOKUP, some of you already know, you learn from database or data table processing, you are trying to search for it, right? So the table will be a CDF table like here on the right side. Number one, it has two columns, right? The CDF first, then the X value, the second column. Number two, the CDF values have to be sorted, starting always from 0. That's the VLOOKUP requirement. Okay, of course, another differently written VLOOKUP can specify that you always end at 1. I mean the other way around, right? So notice that we didn't really have to bother with the ending number 1. We know CDF adds up to 1, but we don't have to write that because it's by default 0.7 or higher, we will just return, or VLOOKUP will just return 11. So always start with 0 and keep increasing in that sense. Okay. In R, we also have similar functions. In fact, in Python, in various other languages as well. So the source of random numbers from 0 to 1 uniformly distributed is random R uniform, or RUNIF, but it's actually R uniform. Give me one number, and if you don't specify from where to where, it is automatically from 0 to 1 by default. If you want it from 100 to 200, then you say 1, 100, 200. But remember, if we want to do this, the range of the uniform distribution has to be from 0 to 1. So once we have this number, we assign it to Q, for example. Next, the inverse CDF for normal in R is just Q norm. We feed the Q, the value generated by the uniform random number generator, and we enter the mean, let's say 100, and SD is 10, and out comes another random number. So if we perform this 1,000,000 times, then we have 1,000,000 normally distributed numbers. How do we check? Plot the histogram, straight away you see. For continuous uniform distribution from A to B, we apply, well, this is guided by mathematics, so it won't change. We apply this function A plus B minus A times Q. And finally, for looking up a table, right, of discrete probabilities and hence a table of CDF, we can represent the CDF table in R using a data frame. A data frame is like a portion of Excel's worksheet, so it's like a 2D table. And we can title it first column CDF, second column X. So after generating Q, we plug that into here and say that look up, or we tell R, look up the DF table. Let's just call this the DF table. Look up this table. Look up this data frame table, right? Under the column CDF, right? Under the column CDF, look for it where it is less than or equal to Q. So if you give 0.3, then 0 will be less than 0.3. 0.2 will be less than 0.3. Example 0.3. Okay. So notice here we have another table, right? We are referring to the whole table, and in R, this is row, comma, column. Row, comma, column. So in other words, we are saying identify all the rows such that the CDF column is less than or equal to 3. So we have row number 1, row number 2. So this will be row number 1, row number 2, and the column, right? Because at this point we are extracting the whole row, including CDF and the column X. So in the column section, or the column parameter here, we are telling R to only look at or return to us the X column. So the result of this whole thing is going to be two numbers, 9 and 10. 9 and 10. Yeah. Then what happens? Well, R looks at the tail here and says, give me the last number. In other words, the largest number that satisfies the less than equal to Q condition. So tail means give the tail end of the vector. So give one number, and so that number is going to be the last number, so 10. So this is simulating the VLOOKUP in Excel. That's it, right? So you just basically do a condition and extract the columns, and finally the last cell. That's all. What are the applications? Well, first let me move myself away. Okay, so the applications, many, right? So I've already named a lot. Flight simulator, games, Hollywood movies, computer simulated generated movies. In a way, AI is also, or AI generated movies is also part of simulation. But it is easy to get confused between simulation and visualization. Visualization, the main idea is to watch. That means is to see it. Sometimes is to believe it, because seeing it is believing it. But sometimes is that we have generated a lot of data, and our eyes are not very good at looking at masses of numbers. But when we can visualize them, straight away we can capture 3D projections. Straight away we can capture some spatial relationship between measurements. Straight away we can identify the patterns. For example, when you look up the sky, some people might say the cloud looks like a face, the cloud looks like an aeroplane, right? So how come we get these descriptions? The clouds are definitely not following the aeroplane's design. More because we can identify patterns with some similarity even, right? So close by, similar looking patterns, we tap our eyes and brains to perform the analysis. So visualizations, the idea is to use our eyes and brains as computer. That's why we need to visualize and render the data as faithfully as possible. Simulation, on the other hand, is to generate, right, the data, right, based on microscopic understanding of the details, and we don't understand the macro behavior when a lot, and sometimes we talk about billions of these micro entities are put together, and they interact, and they mutually affect each other in a random and yet not so random way, right? Which is controlled randomness, which is what we have been talking about CDF and InvCdf. So SimCity, if you have seen or played this game, or just YouTube it and see, allows you to, or the player, to build a city, right? By allocating resources, by building armies, by building businesses and so on. But does it mean that when you build businesses, you become rich and the city will flourish and more people will come because there are opportunities? Does it always mean it's successful? If it's always successful, then how come not all cities will flourish in real life, right? So there is certain kind of randomness, and randomness interacting with randomness. And when you, for example, decrease the tax, will people immediately flock into the city to build businesses and then make your city wealthy, right? So when you reduce the tax, there is a chance that some people will come. That part will be simulated, right? And you need InvCdf. So here in the business world, right, in all areas, medical science, games, flight simulations, military, right, many areas we're using simulations. But let's come back to lean and operations. Now, a lot of times when we perform measurements, because you need to gather data, we might think that our measurement is like this. For example, we measure the molding machine and we look at it because we're new to this machine. We think it's a machine, it looks robust, looks new, looks new. So we have a biased impression. We think the molding machine always takes 5 minutes to mold, 5 seconds, for example, to mold any flow units, mold the metal. So as time passes, we think that it always molds with 5 seconds, more or less precisely, right? We think it is a horizontal line without any noise, when actually it is more like this, this one. So that as time passes, if we measure the molding machine's time to mold each flow unit, each metal piece, sometimes it's 5.1, sometimes it's 4.8. Occasionally there will be a spike, yeah, and that doesn't sound unreal. That doesn't sound unreal because occasionally there may be some kind of misbehavior that only comes about every 100 pieces, right, in the machine. We don't know, right? There may be a gear inside or some software, self-diagnostic or whatnot inside. Or occasionally a big truck that is like 6 tons or 10 tons truck, right, rolls past the road outside our factory and so cause a little bit of a shaking of the earth. It does, right? So minor, and yet it can be felt by us. For the machine, of course, it can even be causing this spike, right? So that it will just take a little bit longer, extra, 0.2 seconds or something. So you end up observing the spike. Maybe, I don't know. So we are talking about real life, right? So when you measure the time it takes, you can actually observe a lot of noise. And it doesn't have to be time. It can be the result of the molded metal pieces that sometimes, I don't know, molding, right? You can do various measurements. So maybe you're measuring the gap. The gap is supposed to be 5 cm gap after molding. But some flow units, you will get a 4.9 cm. Some flow units, you get 5.1 cm. That's not impossible again, right? If you measure with higher precision, you might see even more noise. And so, what do we do with that? What do we do with that, right? So if we plot those sampled time measurements or even gap measurements, the thinking is that the histogram should be a single stick because 100% of the measurements should reflect 5 seconds. When actually maybe 68%, 63% of the measurements will be around 5 seconds, still with a tolerance. All right, some 30%, roughly 15, will be larger than 5%, 5 seconds, shorter than 5 seconds. That's true, right? Yeah. So if you measure more, or if the machine is misbehaving more, or if you measure with higher precision, so it's not 5.1 to 4.9, but rather 4.99 to 5.03 seconds. If you measure with higher precision or high-speed camera, then you can see that spread, right? So that's what we are talking about. And when you systematically build processes, where is my process? Yeah, okay. So for example, a resource or a process of one resource repeats a particular action 3 times on the flow unit before it can continue. So that's why you need to do 3 times X. So in this case, for example, I don't know, washing machine. Yeah. So a washing machine has to rinse a load of laundry. Okay, rinse and dry. Then rinse and spin, right? Rinse and spin, rinse and spin. So a particular program on this washing machine has a super clean step, right? Where super clean means rinse, then spin to dry out, then rinse and spin, then do that, repeat 3 times. And that's when you have a random variable x measuring the rinse and spin, right, the time it takes. And so since the software controls it to repeat 3 times, so the total time will be 3x. So by design of the machine, you end up having a 3 times x random variable instead of x random variable, right? Same thing, if we concatenate 2 resources, so perhaps you are saying, for example, you have a washing machine and a dryer machine. So after spending x minutes, x hours in a washing machine, you then load it up into the dryer to dry for another y hours. So the total time to get your laundry done is x plus y, right? So these physical building up of the resources, sequential parallel connection of the processes, of the resources to build the processes, end up, at least for the time, right, measurement, end up will make constant multiple or additions of these variables. But then when you calculate based on statistics and probability theories, the variance of the 3x variable is 9 times, that means 3 square times the variance of x alone. So it's like disproportionately magnified in terms of the variance. Same thing, the variance of x plus y turns out to be variance of x plus variance of y if x and y are independent. That's our knowledge from statistics. But if not, then you have to add 2 times of the covariance of x comma y. And covariance can be plus or minus. Covariance can be plus or minus. So if x and y end up having positive covariance, then you're also increasing the variance of the resulting sequentially linked up 2 resource process. And why are we talking about variance? Recall that the variations are bad, right? Variations are bad. So variance is a direct measurement of variations. And so higher variance just means bad, more bad, right? And so you want to be aware of that. So thanks to the knowledge from statistics and probability and how we can build the statistical model of this, we can then adjust or know that the variances are there. And then when we simulate, we can then ensure that we don't have unrealistic simulation model. For example, constant, no fluctuation, 0 standard deviation. That would be unrealistic, and you are better off not even doing the simulation because it will tell you what you want to know already. So remember, when we do simulation, we always want to know always want to know a macro perspective. Macro can be the weather, right? The climate. Is it going to rain? That's the macro outcome. The micro will be the locally measured wind direction all over Singapore, for example, right? The locally measured humidity all over Singapore, and then we form a picture, then we make a simulated projection, whether it will rain or not rain, 2 hours later, 6 hours later, tomorrow. So that's the macro answer. All right? The locally familiar or locally understood principles and measurements are known, are factual. We're going to rely on that. And the locally known principles, they will be subjected to variations. And when we put millions and millions of them together, they start to interact, right? And the simulated outcomes will then process these generated random numbers in a way that follows the known principles. For example, in weather forecast, for example, we'll follow the physics laws, how the wind interaction or the geographically known behavior of wind and particles So all these are the principles and rules that we know very well, we put in, right? And then we want to, our outcome is the macro answer. Will it rain tomorrow? Okay. So in discovering new drugs in pharmaceutical companies, one way of applying simulation might be that we know all the amino acids, the chemicals, the compounds very well. We know individually very well, right? We know how they are made up of, how even the shapes look like and all that stuff. But when put together, sometimes by random selection, we just like cook them together, right? Is it going to be a drug or a poison? First of all, if it's a poison, let's rule it out, right? So by simulation, we can put them together. First of all, can you put them together? Will the chemical compounds repel each other, or will they be very stable in terms of being combined together, right? So that we can use simulation to tell. Once it can be combined together, would it be a poison? We can tell. So we can then simulate, right? And then will it be effective or not? We can also predict. But ultimately, we have to do actual clinical trials to see if it is effective on actual human, right? But when we come to that stage, we have already eliminated thousands or even millions of impossible, invalid, so-called new drugs that don't work, right? So we have eliminated poisonous combinations. We have eliminated ineffective combinations because they become water, they become vitamins, they become basically not what we want. Maybe it's for COVID-19 uh, uh, medicine, right, to help reduce the fever, and those combinations don't help reduce the fever. So maybe it's vitamin, which is good for the body, but that's not what we are after, right? So we want this macro outcome. Can we come up with an effective and stable new drug? So simulation can test all these, because if you ask a scientist to sit down, we have to think of how to combine the drugs, right? But we think too much. So before we even combine them, will start to apply theories to try to eliminate certain combinations that upfront don't make sense. Computers don't do that. Computers just put them together first, right? And then calculate, right? Test whether they will be stable, test whether they will be poisonous, test whether they will be uh, effective, and if it is effective, put them aside. Is there another better one? Is there another more effective one? And computers will just do that, millions and millions of times, and we just let it run. That's why simulated results, they are often also very discovery oriented. I mean, apart from Hollywood movies and all the computer games that are so realistic and so fun, that's the fun side of things. But then there are also serious side of things of discovery, right? For lean processing, sometimes it is that we want to do various redesign of the process flow. And if you actually move the machines and the configurations in the factory, run a few months to gather data, then change again, that will be so disruptive and so inefficient. You're going to have downtimes, which means you're going to ask your customers that to not buy from you. You're going to push your customers to your competitors, and they probably don't come back after you are done with your testing, right? Because you're not taking care of your customers, you're just doing internal tests. What if you have a model of various machines and their performances and people of the workers and all that, right? And then you kind of put them together in a software. There are many such industry software that perform simulation, right? Precisely because we want to test out if it is better to rearrange the machines another way, if it is better to uh, not have a conveyor belt mass production kind of design, but rather let's try out a job shop scenario or micro cells, right? So where each worker is responsible for 4 to 5 machines. And after they are done, they are being wheel carted to another job shop to continue the processing. And each job shop can produce multiple products, even though they are in lower quantities. Which way is better? Now, you cannot try out with actual factory or build a actual job shop just to compete with your current conveyor belt scenario. So what are you going to do? It's like not possible. That means we never should. How should we actually do this, right? So if you go by planning and calculation, it's very um, number based, right? It may not take into account a lot of other situations. For example, will the machines block each other? Will there be enough space? Will the worker have enough space to move around? Will the wheel carts have enough room to maneuver, and so on and so forth, right? So you need to simulate, almost like playing a computer game, except it is not for fun. It is for real, right? And specifically describing your factory, and your factory in Kuala Lumpur in Malaysia, for example, not in China, Shenzhen, not in Japan. You know, the environment, the you know the climate, the temperature, everything will be different. So simulation software allows you to do that kind of customization so that the result will be very tailored to your specific environment. That's the whole point. Yeah. Okay, so those are the applications, many of them, and industry applications to try out configuration, new flow of your flow units, yeah, new route for the processing, new machines, doubling the machines. Would it save time? Right? Will it reduce the flow time if that is the objective? So all these questions are best answered by just running those models in a industry-oriented simulation software. It's like a game software, right? But applied to industry. Arena, for example, is one such software, right? So, of course, there are many more, and that's the reason why simulation is so generally accepted, because it is saving costs, allowing for better as in higher quality planning, and also very efficient. If you don't like it, just destroy the model, come up with a new model, and then you're done. Okay, so here I want to just introduce two quick uh, distributions in addition to what we have discussed. We have discussed the table distribution, normal distribution, continuous uniform distribution. Just two more very useful distributions that I want you to be aware of. One is the exponential distribution. Right, we write it as this, and just like normal and uniform, we need to supply parameters, just one parameter, the lambda, right? And of course, you will recall, lambda is the average arrival rate of the customers. Just giving that average arrival rate, for example, 1.5 customers per hour, 2.7 customers per hour, just entering one number will give us the exponential distribution. So the exponential distribution looks like this. This is the PDF, and the PDF function is here. Okay, what is more important is of course our CTF. Now, because the function is so simple and so effective, so relevant in describing the inter-arrival times of customers who don't collude. So for example, retail shops. Retail shops basically will welcome customers, but not all customers will come at the same time, right? So time and again, one customer comes. After some time, another 1-2 customers come. So the time gap is the inter-arrival time. And the time gap, if you measure them and plot them as a histogram, you will see something that looks like an exponential distribution. Okay, maybe minor differences here and there, but generally it's like a decaying shape, right? And it is being observed everywhere that essentially you might as well not have to live with these, jagged discrete probabilities. You might as well just replace that with the rate curve. It is infinitely smooth. It is well described by an exponential function, right? So it's a little bit less real, but it is so easy to manipulate because the CDF is just the integration of this, which can be done readily, and you have this final form here. The final form of the CDF is also so simple that you can literally do the inverse yourself, right? By making the x the subject of CDF of x. So Q here is the CDF of x, and when you perform this calculation, you are performing the inverse CDF function for the exponential distribution. So what has it got to do with that? Remember, the inverse CDF function will massage the randomly generated real numbers 0 to 1 from the computer chip into an exponential distribution function. Therefore, every single number, hey, where's my mouse again? Every single number that comes out from here, for example, 1.5, 0.7, 2.3. Every single number that comes out from here is going to be the time gap between two consecutive customers. So if we have a simulation software that kind of animates, right, like a game, that animates a customer coming into the shop, kind of like in real time, then the software has to know when is it the right time for another customer to come into the shop so that it looks natural. It cannot be pre-programmed to have a customer come in every minute, predictably. That will look so unnatural that whatever you're going to calculate, like the profit for the day, the number of items to be sold, will be very predictable and completely unreliable because it is through such randomness that you want to let computer run a million times, then you gather some sort of an average number of items sold per day, average profit per day. Yeah? So to kind of like accurately randomly generate the time gap after the first customer has arrived till the second customer arrives, what's the time gap? So when we do this, we get 1.5 minutes later, another customer arrives. 0.7 minutes later, another customer arrives, and so on and so forth. So now computer has a very accurate idea of how long later to have that animated customer come into the shop. And of course, if we don't want to watch it in real time, we can accelerate it, indefinitely, right? 10 times. Can you run this 10 times faster? I don't want to watch the animated movie, but just calculate, 10 times faster so that I know the profit at the end of the day. So you can do all kinds of things. So long as the time gap between consecutive customers, they are accurately and correctly reflected in your simulation, right? So thanks to the inverse CDF function, you can do this. So exponential distribution, very useful, or very, very useful in reflecting incoming customers' inter-arrival times. Similarly, service times are also observed to be, in many cases, exponentially distributed. What does that mean? Service time is the time it takes to process the customer, right? So for a molding machine, it will be the time it takes for the molding machine to complete one unit. Now, for machine as resource, as the server, it tends to be more normally distributed because it is designed to have certain performance, right? And it's very mechanical, very electrical, very high precision in many ways compared to human. So for the service times to be exponentially distributed, it is likely not going to be a machine or a mechanical device. So it's likely to be a human. And for human, we're talking usually, right, about services, human to human. So in those cases, for example, a bank officer serving a customer, a customer at the bank branch. And if you have been there before, you know that they offer various services, right? And the customer officer upfront wouldn't know until she says, "Hi, good afternoon. How may I help you?" Then the customer will say, "I'd like to withdraw money, or I'd like to open a new account, or I'd like to open a forex trading account," which takes a lot of time because you have to submit documents, verify, and all that, right? So the time it takes to serve the customer can vary from 5 minutes to 15 minutes or longer, maybe, right? So then, how do you mimic that kind of transaction? Again, if you pick normal distribution, then likely your results are going to be not so reliable because it is equally likely for the customer to have short transaction time and long transaction time. But that tends not to be the case because for extremely long transaction time like these, first of all, it is possible, it is non-zero probability, but it is also very unlikely. So once in a while, you have someone asking to do international forex trading, so which will take 20 minutes to process or even longer. But most of the time, people queue up to withdraw money, deposit money, right? The short transaction times most of the time. So it'll be something like this. Can you see why now that the exponential distribution also describes very well for this kind of situation, human to human service oriented service types? Again, in a factory, if you have a machine molding metal sheets and you apply exponential distribution, first, the justification is wrong, and the result that you get most likely not reliable, and so why run the simulation in the first place? Okay, so just take note that exponential distribution very useful for describing inter-arrival times of non-colluding customers. They don't collude, they don't call each other, let's go for the chicken rice stall together today, right? Then that is not described by by exponential distribution. And service times, human to human, service-oriented basis, then exponential distribution tends to describe the service times very well. Okay, the next distribution that I want to talk about is the triangular distribution. Of course, it starts to look a little bit scary, but actually the most complicated part is just square root, right? No big deal. But you also don't need to worry too much about the form of the formula it takes to calculate the CDF and the inverse CDF, because just like inverse CDF for normal distribution, super complicated, we just run the relevant inverse functions in Excel, in R, in Python will do, right? So here you can of course just program a function yourself and treat that as the inverse CDF for certain ranges. Now, having quickly introduced the format of CDF, inverse CDF, just to have a feel of it, let's look at the shape of the triangular distribution. Not surprisingly, it looks triangular, and it is pretty adjustable by 3 parameters, A, B, and C. So just like exponential distribution, we need a parameter. The triangular distribution needs 3 parameters that are very visible. Visible because they are clearly and unambiguously found on the x-axis, A, B, and C, right? So the A and the C, they are a bit like the uniform distribution, the left end and the right end. The B additionally tells us where the mode is, where the peak of the triangle is. And thanks to B, the B here does not always have to be the average of A and C. In other words, we don't always get an isosceles triangle. It can be a skewed triangle, which is very nice. Okay, so here, how nice is the triangle distribution? We have been talking about normal distribution, right? And you know normal very well. Now, suppose if we say that we have a service time that is normally distributed. Okay, so a molding machine. So a molding machine is normally distributed with a mean of 5 seconds and a standard deviation of 1 second, which is a lot, right? 1 second is about 20% of 5. Oh, I'm not seeing the normal distribution here. Okay, so here you see it. Okay, so like this, what's wrong with that? Not quite in theory, but when it comes to simulation, you are going to actually generate the service times of this poor machine, poor molding machine, right? Average is 5 seconds, sometimes 4 seconds, sometimes 3 to 1 seconds. But when you do InvCdf, there is going to be a small chance that you get minus 2 seconds, minus 10 seconds, and minus 5 million seconds. Small chance. Okay, so not impossible, not very likely, but possible. Right. So now, on the other side, your machine normally produces a flow unit, a molded steel plate or something, in 5 seconds. But because it's old and clunky, sometimes it takes 6 seconds, sometimes 10 seconds. But because you're saying that the time it takes follows normal distribution, a correct InvCdf of normal distribution can sometimes produce 1,000 seconds, 10 million seconds, 100 million seconds. Now, it's not impossible. It's very rare, but it's not impossible. Now, for software, you have to cater to all possibilities. So now, suppose if the InvCdf for this normal generates 5 or 50,000, just out of this, once in a long while, you happen to get that long while moment, and it generated 50,000 seconds. What happens to your software that mimics this molding machine? Instead of ka-ching, 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 it will be like frozen because it is trying to execute the 50,000 seconds, and it stops moving. It seems to be stopping the movement, but it is executing dutifully the 50,000 seconds that the InvCdf just generated. What happens if it is if the InvCdf generated negative 20,000 seconds? Then it may just crash your entire animation or the visualization of that molding machine. And so, as a software, if you write that software, you have to handle these cases. So what are you going to do? You're going to check whether the generated timing is less than 0. If it is less than 0, then you're going to truncate it, but it will start to look a bit absurd because you're losing the left tail and the right tail and so on. So all these make the simulation software a lot more complicated because you have to handle the tails, and if the numbers are handled properly, the tails are handled properly, the numbers still don't give very reliable outcome. Yeah, because essentially everything from 0 to negative infinity, they are lost, they disappeared, they are gone, right? So it's very weird that the distribution doesn't add up to 1. Now let's flip back to the triangle distribution. If I now say that the molding machine, right, uses the time intervals from 3 seconds all the way to 3, 4, 5, 6, 7 seconds. Okay, and B is 5, so 3, 5, 7. So 5 is actually right in the middle, right? So we should see a very balanced triangle, more because we think the molding machine it's not very good, it's old, that's why the range is from 3 to 7, right? And but we are not sure whether it's biased more towards the lengthier time or the shorter time, so in the middle, and that's fine. And when we do inverse CDF, we will never get any molding times that are going to be lesser than 3, or for that matter larger than 7 seconds. So that's fantastic, because it is guaranteed by birth, by the design or the use of this triangle distribution, that our inverse CDF will never give us a weird number that we have to check again. So our simulation will just take the inverse CDF random number and draw or animate or simulate or calculate and continue from there. We don't need to truncate. We don't need to worry what if the timing is very large, what if the timing is negative. Never, right? Because so long as we don't sabotage ourselves by entering -3, we enter 3 here, right? And we don't enter -3, then we should be fine. So it's very controllable, very nice, as a replacement, as a practical replacement of normal distribution. Okay, so when it comes to simulation, triangle distribution is a very nice replacement of normal distribution when we choose our B here to be equal to A plus C over 2. That is in the middle of A and C. Yeah, because then it's symmetrical, perfectly symmetrical. What's even nicer, right, for triangular distribution is that it doesn't have to be unskewed. It can be also lopsided. For example, in this picture here, B is shown closer to the A than C. That means it's skewed to the right. So to reflect, for example, income distribution, to generate, like for example, a retail store, right, will welcome customers. If we want to say the customer that comes in has high income or low income, right, so we should randomly assign. But is it true that half the time is high income, half the time is low income? No, it's not half, because if you look at any population income distribution, it's always skewed to the right. Skewed to the right, you can use various simulations, distributions like chi-square or F distribution. But again, while it doesn't have negative infinity, it does have positive infinity. Right? So another nice candidate for replacing that kind of problem is a skewed triangular distribution, or basically triangular distribution, right? With a B that is closer to A than C. That's all. And so you are guaranteed to never experience a person coming into your retail store with a negative income, right? So another person that has $60 trillion of income every year, right? And I think the richest person on earth doesn't have $60 trillion of income per year. But that remains possible if you have an open tail towards infinity. Yeah, right? So we don't need to worry about those when we have already, by construction, a closed end, closed tail kind of situation when we use triangular distribution. So I think for all these reasons, I like to introduce this new kid on the block, triangular distribution, and hope you will find use of that. Okay, I've mentioned a lot about applications of simulations. Yes, it can sound a little bit boring and not so exciting when we apply simulations to lean and operations and factory configurations, manpower projections, profitability, if we reorientate our process design and various things like that, right? But of course, if you are the manager in charge of profitability, responsible for P&L, then you will be very excited at such a technology that reflects not a general theoretical prediction, because you want to know for your factory, for your operation, for your process, will it make sense, right? So with simulation, you tailor make, you kind of create a digital twin of your process, of your factory in the simulation software. Then you run it, and of course you will have high confidence that if the software says yes, that's good, if you reconfigure your conveyor belt continuous production process into a job shop cell-based configuration, it will be much more profitable. You will have more confidence that it is a reliable conclusion, and then you will execute on it. Right? But just to jazz up the excitement a little bit, simulation, of course, is used in many profit-making ventures, such as games, right? So the games these days are looking so realistic because they have very powerful rendering engines, and they are able to not just have very robotic arms and very sort of move the fixed picture kind of situation. They can actually animate the 3D model right on the fly and make the various game very exciting. Like in this example of a car racing game, you almost feel like you're driving the car yourself, right? Inside the driver's seat. And other places, the monsters that come attacking you, they form teams, and the teams don't charge at you in a very military style, like everyone move one step forward and next step forward, and not like that. They will just like bees, right, surround you all over and in the asymmetrical manner, and all these you need the XY axis coordinates to be both coordinated and yet random. Well, you want to show team formation and not symmetrical team formation, so symmetrical that it looks very artificial and fake, right? And if a game looks artificial and fake, is predictable and doesn't have randomness, then it is too easy, therefore nobody wants, or too tough that nobody wants. So your game has to be calibrated at the right kind of randomness. And that's why InvCdf, like the lens that we have to focus the sunlight into a spot, depending on how hot we want it, we will move the lens accordingly. Same thing, right? In game, especially games, where you want the randomness to be tuned to the right amount of difficulty, you want the distribution to be nicely shaped so that the random numbers that come out from the chip will be focused into the right level of difficulty, and that is translated into the right kind of distribution curve. Now, of course, in the movie industry, you want, or of course, depending on what kind of movie you're doing, for even sort of a basic level of cartoons these days, they are generated with a lot of realism. For example, just look at this static picture of Disney's, what do you call that, Cars, I think, yeah. To draw the trees, one way, in the past when the simulation is not that, or rather the computers were more expensive and not that fast, you want to take a picture of the actual tree and then maybe Photoshop it a little bit and then put as background. But these days, the trees themselves can be modeled and generated. Here, you don't generate the leaves, but you know that the greens, look at the color green here, right? Some are darker green, some are lighter green. We know that. But then which pixel should have darker green, which pixel should have lighter green? To make it look very natural. And look at this, right? So the end result is that some pixels are darker green, some pixels are light green, so that they reflect some sort of like new leaves growing over older leaves and all that. And it looks so natural, so beautiful. Okay. In earlier days, without simulation, right? Then you have to just draw patches of the same color, but look at the year here, it's not looking as natural, and we kind of accepted it for kids, right? Because the year here is just one patch of same color, and that has got no light reflection, no whatever it is, right? It doesn't look very natural. Look at the face for the Frozen, more contemporary, right? So from Disney as well. uh, I should change color to red maybe. Look at the face here, just this Frozen picture. This Frozen picture, the picture is not moving. Just looking at the face here, you look at the face and you can immediately spot gentle patches of more reddish kind of cheeks here, the cheeks here, right? Than the forehead, which is a bit fainter, but yet still looking a little bit pink to reflect the kind of like a bit of the maybe it's the frost bites or something, right, on the skin. And um, that natural gradation of the pink to lighter pink or to even a tint of whiteness, they need to be simulated, because for hand-drawn kind of situation is not going to be as productive and as accurate. So how does one decide? How does the algorithm decide to randomly generate the pixels with suitable levels of pink color, right? One way is normal distribution, right? Because the pink color is most of the time pink, right? Sometimes a little bit less pink, a little bit more white, a little bit more red, and most of the time is scented pink color. So that alone requires some sort of a randomness. And same thing here, if you look at the dress itself, okay, um, it is also having some sort of noisy mix of maybe white, blue, and pink, a little bit of red and purple. So which pixel should be pink, should be purple, should be blue, should be white? Again, you need randomness, right? So all these are uh, visible results of simulation, much more attractive, much more exciting, much more visually pleasing. But nevertheless, they are there for a purpose, to make it look more natural so that the story is more attractive to kids who are very picky. They want the image to look very real so that they are excited. So to make that kind of to achieve that kind of standard, you need good InvCdf to achieve the right level of distribution for the colors, for the choice of colors itself, right? And then the positioning of the snow patches, right? And I mentioned in the cars just now, the colors of the leaves, right? And the positioning of the light greens and the dark greens and so on and so forth. So a lot of times we need to have controlled random numbers. And hopefully from this lesson, you get a taste of how simulations are done. Anytime you have simulations, whatever it is, flight simulation, industry simulation, games, movies, whatever, you have to generate controlled random numbers. Okay, maybe you are now even itching to try out yourself, right? So you can go ahead and try them, and then see what kind of business ideas you can come up with. All right, with that, we will come to the end. We have come to the end of this video. Thank you for your attention, and I'll see you in the next video.